All right, guys. Today we are going to go ahead and begin Unit 5. Which Unit 5 is going to be the start of like the second field of calculus that we have. So calculus as a field is mainly divided into two main areas. We have differential calculus, which is basically what we did in Units 1 through 4 plus limits. And then we have what's called integral calculus, which is going to be from now until most of the way through spring semester. The link between them, like the idea of limits, is what allows us to have both differential and integral calculus. We'll kind of join the two together when we get to Unit 9, which will be differential equations. I did want to show you this unit. I know y'all probably have a busy 2 weeks, and I'm probably about to make it busier. This is the shortest unit that we have. It is all skill-based, like there's not a lot of, well, really there's no applications, no like critical thinking stuff. Like it's just like, just do it so that we can do the harder stuff basically coming in after Thanksgiving break and then moving into second semester. It's only 4 topics, 4 homework assignments. It is a little top heavy with the workload in the first half, just being honest. But again, it is very much like skill based. Like these are not going to be problems that take up like half a page. They're very much like 1- and 2-step problems for the most part. Today we're going to be looking at something called Riemann sums, which I like to say, like if you can find the area of a rectangle and a trapezoid and add them together, then you can do Riemann sums. Tuesday we're going to be doing something called the indefinite integral, and then Wednesday we'll be doing something called the definite integral. But honestly, there's not much difference between the indefinite and the definite. So there is a lot of overlap, especially with like homeworks 2 and 3. And then your quiz, this usually is one of the easier quiz, I'll put it that way. Just because it's very, very straightforward, not a lot of applications again, because it's just going to be the skills and the introduction to this idea behind integral calculus. We don't really get into it much more in depth until we learn some like other techniques of integration after Thanksgiving, but really the bulk of this topic is coming in second semester. So looking at our notes, I shared these with you, but again, you can kind of take notes with whatever you want. There is one page that's just going to be all the derivative and integral rules that we should know by the end of the semester. Obviously, we already know all the derivative rules. We're going to be looking at integral rules starting this week. That's what that little symbol represents. But today we are going to do a topic called Riemann sums. And so before I look at Riemann sums, I just want to kind of talk about like where these are coming from and like why they're important. So I mentioned previously that there's really 2 main topics in calculus. The first one is one that we've already looked at. We've looked at differential calculus, which is calculus that deals with derivatives. And we know if we think all the way back to August, honestly, this idea of the derivative came from if we have, say, like a secant line, the slope between 2 points on the graph, that we can take that secant line and then using our idea of limits, that secant line can become a tangent line. And that's really what calculus is all about when we're talking about differential calculus. That's kind of like the problem that was studied early on by like Newton and Leibniz, and from there arose like a whole bunch of other applications. We've looked at some of those applications. We looked at curve analysis, intervals of increasing and decreasing, concavity, points of inflection, extrema, and then we looked at some other applications too, like related rates and optimization. There's of course more, but that's what we kind of looked at when it comes to differential calculus. Integral calculus, which was also developed by Leibniz and Newton, they focused really more on differential calculus. Riemann was a big one that was focusing on the study of integral calculus. And the idea behind integral calculus is if we have some function, how can we find the area underneath that curve, which we will see has a lot of other applications. I think it's a lot cooler applications than derivatives in some ways. It's going to be kind of unique that we can associate like tangent lines and areas are in many ways related. But if I just ask you in general, hey, find the area underneath that curve. Like obviously this shape is not some geometric formula that we know. So what would you start doing if you had to estimate the area underneath that curve? You can split up the shapes that we know. So like if you're doing this on your own, like obviously you may like say, oh, this part looks like a triangle, another part looks like a rectangle, and kind of divide it up that way. What we're going to do just to be consistent is divide it up with like the same shape over and over again. So for example, I can divide it up into some rectangles. Again, not the best approximation if I use 3 rectangles, but I know I can keep like changing it to find like a better and a better approximation. For example, right now that's 3 rectangles. I have some overlap for the most part. If I wanted to have more of an exact area, what can I do with the number of rectangles I'm finding? I can keep finding more. So like instead of maybe finding 3 rectangles, I might say, okay, let me say I want a more exact area. So let me just do a bunch more smaller rectangles. I'm not going to draw these all the way across. But we know that we can kind of finding like more and more rectangles that will fit underneath the curve a little bit better. So the idea behind integral calculus is we do have this thing called the integral, which is actually going to be the sum of an infinite number of rectangles underneath the curve of like an infinitely small width. But what we need to understand first, there are going to be lots of times where we may not have the exact function. Maybe we have like a table of data, or maybe we just have the graph but not the equations. And we want to find a way to estimate the area under the curve. We have 4 ways that we're going to estimate area in this class. 3 of them are going to be using rectangles, and 1 of them is going to be using trapezoids. I'm going to kind of just go through like how I would draw them, kind of the words used for them, and then we'll finish with like 3 examples of approximating these problems. So in this first one, I have like some basic function f of x, just made it up. And we want to approximate that area I have shaded in yellow. Things that will happen with these problems, so this is called a left rectangular approximation method. Oftentimes we would just abbreviate this as LRAM. And what that means is we are going to be drawing in rectangles from the left-hand side to approximate the area under the curve. Normally in a problem like this, they would tell you how many sub-intervals to use. Like we know the more rectangles we use, the more accurate the area is going to be. But they will give you like sub-intervals, which is basically going to tell you the number of rectangles you're using. For the sake of just kind of seeing it, I'm going to use 3 sub-intervals, just so you can kind of see how these would be drawn. So I am doing a left-hand approximation method. We will take the area that we want to find, divide it evenly into 3 rectangles. Sometimes it's divided evenly, sometimes it's not. And when you're drawing in 3 rectangles from the left, your rectangle's height are going to be defined by the left side endpoint on that subinterval. So in these 3, that first rectangle, again, starting from the left, going up to the top and then over, there's 1 rectangle. This middle interval start on the left-hand endpoint, up and then over, and then this last interval start on the left, up, and then over. So when you're doing a left-hand approximation method, you're basically determining the height of the function from the left-hand side. So we know that basically to approximate this area, like it's not going to be the exact area, like all these rectangles are kind of over the function, so it would definitely be an overestimate. But for the sake of an estimation, it would be something that we can use. I like to tell students like Riemann sums is just adding up some basic area products. What do we know the area of a rectangle is? Base times height. Instead of base, I'm going to use the word width instead, just because I think it makes a little bit more sense in the context of the problem. So to find the area of a rectangle, we're going to use the width, and we also are going to find the height. So when I think about the area of a single rectangle, The height, looking at this, is going to be associated with which coordinate on the graph? The y. So it is going to be the y coordinate, so we'll have like some y coordinate times the base, which I'm going to refer to as the width. It's going to think of it, I'm going to put it as delta x. So it's basically going to be the difference of your x's. Like if you have one interval that goes from, say, 2 to 4, the width of it would be 2, 4 minus 2. And then we just want to add all those together. So really, you just want to find those areas and add them together. If you look up Riemann Sums online, you'll see a lot of more complicated looking formulas with like sigma notation and subscripts. I don't see a reason to overcomplicate these. Like we're just adding up areas of rectangles. So like feel free to look it up on your own. My way is going to be a lot easier to understand. So that's left-hand approximation method, or LRAM. We can also look at RRAM. RRAM is going to be done the same way. They will tell you how many subintervals to use, but instead of measuring from the left-hand endpoint, you will be measuring from the right-hand endpoint. So I'm going to go ahead and just do 3 subintervals just to be consistent. Again, you might have a problem that tells you to use 4 subintervals or 2 subintervals. That just tells you the number of rectangles you're drawing. I'm using 3 again just for the sake of notes. And so in left-hand approximation, we start from the left-hand side, go up to the graph, and that traces out your rectangle. For right-hand approximation, you start from the right-hand side, go up to the graph, and that ends up defining your rectangle. So there's the first rectangle, here is the second rectangle, and here is the third. Looking at this one, for this particular example, that estimation would be an underestimate since all those rectangles are under the curve. Called a right rectangular approximation, or RRAM is an abbreviation that we can use for it. So we have the left-hand approximation, and we saw for this particular graph it was all like an overestimate. We also looked at the right-hand approximation, which is an underestimate. I know you can see it in the notes, but if you want to think about a way that kind of balances those, instead of going from the left or going from the right, we can just use the middle. And that's where the third approximation is going to come from. And it is called MRAM, or midpoint rectangular approximation method. And I'm going to go ahead and still use those same 3 subintervals. And what MRAM does, again, you first find your rectangles. Instead of measuring from the left-hand side to find the height, or instead of measuring from the right-hand side to find the height, you're going to use the midpoint of each interval. And that is what's going to figure out the height of your shape. Try that again. So then from the middle, and then from the middle. Again, not the best drawing on my part, but you can kind of see for MRAM, since instead of measuring from the left or measuring from the right, it does provide kind of a balance where you have like some parts are overestimating it and some parts are underestimating it. I don't like how I have that drawn, so I'm going to redo it. I think my pen's just dead. For all those, the midpoint, the LRAM, and the RRAM, you're just adding up rectangles. So like the basic process is going to be figure out what your bases are, figure out what the heights are, and for us, the heights are always going to be associated with the y coordinate. One thing I should have said at the beginning, and it just slipped my mind, but when we talk about the area under the curve, we're going to talk about the area from the curve down to the x-axis. So when I say area in the curve, that's what I'm referring to. The last approximation method we have, so if I kind of compare these 3, LRAM, like, you know, it was an overestimate for this example. RRAM we saw was an underestimate. We have MRAM, which sometimes overestimated, sometimes underestimated. The fourth and final approximation method you have to know for this class is called the trapezoidal sum approximation method. The trapezoidal sum approximation method is nice. because it will allow you to, in some ways, bend a little bit more with the curve, where I kind of think of it like the LRAM, the RRAM, and the LRAM are kind of like pixels, like they don't always line up with the curves nicely. Trapezoidal won't line up perfectly, but it will take into account how the bend of the curve is. So I'm going to draw out a trapezoidal sum approximation method for this one, which we can abbreviate as TSAM. I'm going to go ahead and use that same 3 sub-intervals we've been doing. Again, it's not always 3, that's just the number I'm picking for the example. Still dividing it up into 3 pieces, could be equal pieces, may not be equal pieces. And when we say trapezoids, I know most of us, when we hear trapezoids, we think of this kind of shape as our traditional trapezoid. Definition of a trapezoid, it just has one set of parallel lines. So this shape is also considered a trapezoid. And if I imagine that trapezoid being turned around on its side, then we can draw trapezoids that align with the function a little bit better. So what that ends up looking like, these 2 sides, which are normally called like base 1 and base 2, ends up looking like heights because we've turned that trapezoid on its side, and it will be something like this. So you can see it's not a perfect approximation. Obviously this is a trapezoid, so that is a straight. And so we can see that that does tend to be a pretty close approximation. So you might ask yourself, like, well, why can't we just do the trapezoidal every time if it's the best one? And the short answer is, like, honestly, sometimes you just don't want to, or maybe it's not needed to do the trapezoidal one, depending on how accurate you want to be. So now let's go ahead and look at like what these approximations mean before we actually find them. There's 2 main skills you need after today. The first skill is you need to be able to find an approximation using the approximation that you're being asked of. So if it tells you to do an RRAM, do an RRAM. If it tells you to do LRAM, do LRAM. The second thing you need to be able to do is to know whether the approximation you find is actually going to be over the actual area or under the actual area. So that will help us to answer some questions that will show up a little bit later. So when I think about whether things are over or under, I kind of group LRAM and RRAM together in my head. And then I will also group LRAM and TSAM together in my head. I know LRAM is not a trapezoid, it's also a rectangle, but it behaves in some ways more like TSAM when you're talking about whether it's over or underestimating. So when we're looking at RRAM or LRAM, I think those are the easiest ones to figure out whether you have an overestimate or an underestimate. I don't often memorize these, like I just quickly, like if I'm taking the AP exam, as I did thousands of years ago, I just like draw a quick graph and just imagine what like a left drawn rectangle looks like or a right drawn rectangle looks like. So looking at this first one, like if I have LRAM, this graph is increasing and concave up. I'm just going to draw one sub-interval because we can kind of easily see if it's going to over or under with just one rectangle. So LRAM, again, you start from the left-hand side, go up to the graph. That defines the height of it. And going straight across, there's my rectangle that I would have. That same graph, though, if I'm doing RRAM, we start on the right-hand side, go up, and then move to the right. And we see that this rectangle is very much over the actual graph. Just for comparison, I know I left this one blank in the notes I sent out, so let's just do a decreasing function. Doing LRAM again, if I go up to the function to find the height and then move over to the left, there is the rectangle we see definitely hanging over. So we see that that's an overestimate. For that same decreasing function, if I go up and move from the right, we do see that there's this whole space underneath it where we have underestimated. So when we're comparing LRAM or RRAM, we are actually going to look at whether the graph is increasing or decreasing. LRAM is going to give us an overestimate when your function is decreasing. LRAM is going to underestimate the area when your function is increasing. Likewise, if you're looking at RRAM, RAM was overestimating for an increasing graph, and RAM is underestimating for a decreasing graph. Often what we're doing in these problems is we'll say like, hey, estimate the area using LRAM. And then like the follow-up question would be, is the estimation you found over or under the actual area? And you might say like, oh, well if I use LRAM, I know that this is an overestimate because my graph is decreasing on that interval. So we just have to kind of know what the graph looks like, and then we're able to answer whether it's decreasing or increasing and then over or an underestimate. And so then the other ones we need to know, LRAM and TSAM. For me, it was always easier for me to draw out what TSAM was. It's easier to visualize. And then I just know that LRAM is just going to be the opposite of what TSAM is. Because I think LRAM is the hardest one to visualize of whether it's over or under. TSAM is the one that makes the trapezoid. So if I have, this is an increasing and concave up function. If I just draw one trapezoid, that will give me the idea of what the approximation is. There's my trapezoid. I can see that it is overestimating the graph. I could just check to see whether that's the concavity or the bend of it. So like if I do a concave up decreasing function, you'll also see that if you were to estimate it using TSAM, that trapezoid is going to end up being over the curve, and you have an overestimation. So TSAM and LRAM, instead of being related to whether the function increases or decreases, its over or under is going to be related to the bend of the graph, just by the way that it sets up. TSAM is going to overestimate when your function is concave up, and it's actually going to be an underestimate when the function is concave down. And I can kind of test that out. So here is a concave down function. Drawing in my trapezoid, we see that that slanted side of the trapezoid ends up being underneath the curve. So when it's concave down, we will have an underestimate. Again, for me, LRAM is a hard one to visualize. You'll always have like some part of it above and then some parts below. So for me, I just know that LRAM is always the opposite of TSAM. So LRAM is going to overestimate the graph when you're concave down. It's going to underestimate the graph when you're concave up. And this might be a little bit easy to see. So here's a concave up one. I always have kind of trouble seeing it depending on how severe the concavity is. But there's my LRAM. Like we have some parts over and then some parts under. And then same thing if I have it as a concave down function. I'm going to draw it a little bit more drastic. LRAM would look something like that. Again, the easiest way I think about it, LRAM is going to be just the opposite of TSAM. So for the second part of notes, I just have 3 examples. We're just going to be finding LRAM, RRAM, LRAM, or TSAM, and then for some of them, we'll go back and look at whether it's going to be an over or an underestimation. So first example, I have approximate the area under the graph of y is equal to 2x cubed on the interval from 0 to 8 using LRAM and 4 subintervals of equal width. So I have a chart in my notes right here, and you don't have to use a chart to answer the question. I do think it's nice to have a chart just because it organizes your answers, but ultimately, as long as you have the final correct answer, then that's all you really need to do. I like the chart just because it reminds you like of what you have to find and then doing everything else correctly. So if I'm going from 0 to 8 and I want to use 4 subintervals of equal width, how wide is each of those intervals going to be? 2. So I know that the width of each of your intervals are going to be 2. And if you have a width of 2, like I know you have one rectangle that goes from 0 to 2, another rectangle that will go from 2 to 4, another rectangle from 4 to 6, and another rectangle from 6 to 8. You don't have to graph this problem in order to do it. I think sometimes seeing a graph when you're first starting off makes it a little bit easier. So if I were just to think about what this graph looks like, this is a cubic function that's been stretched by 2. So it does have that basic S curve, but it looks something like this. And basically what we're doing is we are going from 0 to 8. And we are drawing in rectangles to approximate the area underneath the curve from 0 to 8. Again, there's different ways we can approximate it. This problem is asking me to use an Ilm-Ram. So we're imagining the midpoint is what's drawing out these graphs. And then your answer will be basically the sum of the area of those rectangles. Again, you don't have to draw it. In fact, I think that's a waste of time. Because if you know the intervals, you can pretty much figure out everything else. If I'm going from 0 to 2, what x value is going to be used to find the height of that rectangle? 1. We're using the midpoint. Between 2 and 4, we would use 3. Between 4 and 6, we're using 5. And between 6 and 8, we're using 7. If this was an L-Ram problem, I would use 0, 2, 4, and 6. If this was an R-Ram problem, I would use 8, 6, 4, and 2. And so then we need to find the height. Well, which coordinate, again, are we associating with the height? The y-coordinate. So we have the x-coordinate. They give us the function. We can plug it in to find the y-coordinate. So what's the height of that first rectangle? The height of that first rectangle is 2 times 1 cubed. What is the height of that second rectangle? 2 times 3 cubed. What is the height of that third rectangle? 2 times 5 cubed. And then what is the height of that last and final rectangle? 2 times 7 cubed. And then we just need to remind ourselves, what is the area of a rectangle? Base times height. I called it width, but base times height. So my first rectangle is 2 times that, base times height, plus the second rectangle, base times height. Third rectangle, base times height, plus the fourth rectangle, base times height. No need to simplify your answer as long as your final answer is a sum of products, basically a sum of a bunch of areas. Again, you could, but why waste it? Questions on how I found that area using Ilm-Ram? All right, let's try the next one. Here is a TSAM one. We'll also want to remind ourselves how we find the area of a trapezoid. So this one I have approximate the area under the graph of y is equal to 4 on the square root of x on the interval from 0 to 9 using a trapezoidal sum approximation method and the subintervals indicated below. When you see this subintervals indicated below, that probably means your trapezoids or rectangles do not have the same width. And you just need to go with what's provided for you. So one thing about the trapezoid, let's think about our trapezoid formula from geometry. Here is like the traditional trapezoid. Here's the way we're imagining it. Either way, when we think about the area of a trapezoid, what is the area of a trapezoid? Not all, you're missing a part. Divided by 2 times the height. So from geometry, we know that the area of a trapezoid is the sum of the bases average. So basically the average of the bases times the height. When I say base 1, we have like base 1, base 2, base 1, base 2. But these are trapezoids turned on their side, so I like thinking of the formula a little bit differently. So again, these bases are now in some ways like the y-coordinates. So I'm just going to call them y1 and y2. And then what we would normally call the height, since it's turned on the side, that height is going to be like the difference of the x's. So basically like the width of it. So if I'm thinking about the area of a trapezoid for TSAM, I like thinking of it a little bit better as saying y1 plus y2 divided by 2 times delta x, but they're the same formula. I'm just using different variables because of the way we've rotated this trapezoid. So one thing that makes the trapezoidal sum formula a little bit more accurate is by having that slanted side, you're able to bend along the curve a little bit better than with a traditional rectangle. So which x's do we use? For the trapezoidal rule, we're technically using both x's because we have like the base 1 and base 2, the y1 and the y2. They give me the function here. So I can go ahead and plug that into both of them to find the base 1 and base 2 for each individual trapezoid. So like for this first trapezoid, we're saying it goes from 0 to 1. It has a width of 1. The first y value would be 4 root 0. The second y value is 4 root 1. So what is the area of that first trapezoid? It's 1/2 y1 plus y2 times the width. And we can kind of repeat that pattern. And then as long as our final answer is a sum of areas, then it's fine to leave your answer that way. So the second trapezoid, what is your y1 and y2? That first x value will give you your first height. The second x value would give you your second height. This trapezoid is going from 1 to 4. Its width is 3. So to find its area, again, this is a sum, so I'm going to add it to 4. I'm going to simplify these just for the space. 4 times 4 times 2 is 8, divided by 2 times 3, and then plus add this to my final trapezoid. So I have 4 root 4 is one of your y's, 4 root 9 is my other y. The width of this trapezoid is 5. And then I can find its area. So that's going to be 8 plus 12 over 2 times 5. Don't need to simplify it. In fact, normally we don't have a calculator, so it's just best to leave your answer ugly. And you can leave your answer like that. Questions on how I found that trapezoidal area? All right, so this one does have a follow-up question that we need to find. This one does say, is this approximation more or less than the true area under the curve? And then explain your reasoning. So we know that if we're trying to figure out, is it more or less, we first need to figure out, do I need to think about whether it's increasing or decreasing, or concave up, concave down? We did a TSAM one. So does TSAM rely on the concavity or whether it's increasing or decreasing? Concavity. And you would be expected to know like what that graph looks like. Like you wouldn't have to find whether it's concave up or concave down. You should just know, oh, well, this is the graph of 4 square root of x, so it's like a stretched out square root of x formula. If you don't memorize that chart, again, I normally don't. I just think, okay, well, I know the graph looks like that. If I start drawing trapezoids underneath this graph, do those trapezoids end up under or below, under or above the graph? Under. So I know that this estimation or approximation is less than the actual area. How do I know? Because y is equal to 4 on the square root of x is concave down on the interval from 0 to 9. You could also just say it's concave down always, and that would be fine for that answer. As long as it was clear that the interval you're talking about, this particular graph is concave down. So it does bring me to like a lot of these questions on the AP exam, they may not even ask you to use, like they might not even ask you to find the approximation. They just say like, hey, you used MRAM to approximate the area under the cosine of x from 0 to pi. And you would just have to know what their graph looks like because you know your parent functions, and then be able to figure out do you have an under or over estimation on the graph. Questions on that one? They will give you the interval. And that brings me to, you'll never be asked to determine whether you have an over or an under estimation for a function that changes concavity or changes from increasing to decreasing. They will give you one that's consistently something so that you can easily come up with the answer. Last one, go ahead and try this one on your own. Lift off the chart. Again, some people like doing the chart all the time, but if you can come up with the correct answer without doing the chart, then do what works for you. This one's a little bit different. So they just say approximate the area under this function f. We don't have the equation of it, but we have a table. This is one where even after we learn how to find the exact area, we wouldn't be able to. We would only be able to approximate it. And it does say using the 3 sub-intervals indicated. Like if I'm looking at this one, there's one rectangle, a second rectangle, and then a third rectangle. Go ahead and try that one on your own for you. And this is where we will wrap up today's notes. So there's my work for that one. We have 3 rectangles, 3 sub-intervals. We have one rectangle from 3 to 5, another from 5 to 9, and then 12. With this particular table, we would not be able to do like LRAM because we don't know those middle x values, but we could do an RRAM, an LRAM, or technically a TSAM. So we know that the heights of these rectangles are going to be defined by the x-coordinate on the right-hand side of the interval. So like the one from 3 to 5, the y-coordinate with 5 is going to tell you the height. From 5 to 9, the y-coordinate with 9 tells us the height. And then from 9 to 12, the y-coordinate with 12 gives us the height. And then final answer is just going to be the sum of a bunch of areas. So I have base times height plus base times height plus base times height. And you can leave your answer ugly and unsimplified like that. Questions on your Riemann sums? Cool. So your homework is this first homework one. It is only 8 problems. I think for some reason I found in third